Supersonic. JJ Fad would be proud. Imagine we wanted to have a sound source that's moving faster than the speed of sound. So imagine you just had a speaker here that's moving faster than the speed of sound. These circles, and I'll have a simulation for you in just a minute. Let me get that ready. Pause this so I don't get distracted and get the sim ready. Okay. And so what do these circles represent? These circles represent sound waves that were emitted by this speaker at previous times. And we see this interesting shape kind of come out of it. I tried to draw this the best I could. It's not perfect. But we see that there's this angle here. And actually that's supposed to go off the same in both directions. It's not perfect. I'm trying to make this so you can see it. So we see this cone. And actually, let's just get right to the simulation so you can see this better, so you see what I mean. And then we'll come back and we'll do the math in just a second. Share screen 1. All right. See if this, I'm trying to rotate this simulation so you can see that it's actually forming a cone there. All right, and maybe what we'll do is we'll run this program live. Okay, let's just run this program. So you can see that those blue circles coming out are the sound waves emitted by the source, all right? And they end up making that looks like a giant ice cream cone. All right, let's run this one more time, and I'm going to not enlarge the size so it looks a little bit smoother as we run. So you can see it is tracing out a cone, and we can see what happens if we try different speeds here. Where's my source speed? So let's try jacking this up to a higher speed. Whoa! We kind of a different ice cream looking cone. What if we go really close to the speed of sound? How about 6, just barely over? We get a different shaped cone depending on the speed. All right, I think that's enough of that. So my point here is that this is not just a line, it's a 3D shape, it's a cone in space, and these are supposed to be those spheres as it grows outwards. So now, in this case, we see that the angle depends on the speed. So here's our equation that discusses that. The Mach angle, the angle of that cone in here, and making sure I label it correctly, maybe what we could do is erase the bottom half so it's easier to label here. So obviously this pattern will have the wave fronts on top, but that allows me to kind of do this. Let's get rid of that line there. All right, so from right here, in some time, the sound traveled this way. All right, so if you recall, that's the big circle that I just drew. So this is V sound times some time interval t. All right, that's this dotted line right here. Now, in that same time interval, the source moves a little bit farther because it's got more speed. So this red line here is V source times time. And it is the same time interval. The same time interval is required for the sound to go this far as for the source to go that far. And then we've got our angle in here, right here. So the angle that that cone takes depends on the source speed. So if we look at this, maybe we could rearrange that. Theta Mach is equal to sine inverse, and let's see if I screw this up if I'm really tired. Move this up here. We take sine inverse of this. Let's see, we're going to have to flip it upside down. Make sure I don't screw this up. And so we see that the angle inside here, let's see, if the sound and source are the same speed, sine inverse of 1, we should get 90 degrees. That's like straight up, right? And that's what we saw. When we were really close, we had this short, fat ice cream cone. And then if the source is really fast, it's sine inverse of a small number, that's a small angle. When I went really fast, we had a really skinny ice cream cone. All right, and so there's really only one problem that messes with people when we're doing Mach numbers, and that's 17.21. So make sure you try 17.21 and maybe try it without looking at the answer, and then look at the answer if you get confused, and then you'll be done with it.